Looking at section 10.1.2 here. It's on intercepted arcs. This should probably have an S here for arcs. And we're looking at circles. I'm actually working backwards a little bit. I'm not doing 10.1.1 first. That'll be the next lecture. It'll be end number 20. The main reason is because we've already dealt with central angles before, and I want to stick with that notion before we do something kind of completely different or where we're looking way back to triangles again, which again we'll do next time that we give a go around. Next lecture on chords. But this one's intercepted arcs, and I have the definition here, and so we'll go through things. You saw at number 13 on circles, and we had a similar layout, and I'm going to go through some of the previous definitions first. So let's first look at a circle. It's an enclosed shape where the set of all its points are equidistant from the center. So if you look at these 4 points, even A, B, C, and D, they're all the same distance away from the center. These distances are called radii, of course, as you know. So these are all R. And there's an infinite set of points, so any of these are the same distance away. No sides or angles on a circle. It's just, this is what it is. It is a set of points, really. It's this curvy thing that it is enclosed. When you draw any 2 radii, like these 2 right here, let's say I just have these 2 radii, and I draw them out, I have formed an angle, and this is called a central angle, because the radius goes from this endpoint here on the circle to the center. Same with this one here. So central angle is drawn from the center, and any of these here are central angles. Right here, here, and then here, of course. When you add them all up, you get 360 degrees. So I'm going down. I don't know why I have it in this order. Central angle over here. Just like polygons, they are the vertexes on the inside of the circle formed by the circle's radii. So again, you draw 2 radii, like here and here, you have formed a central angle. Let's say this is 60 degrees. Okay. This is 60. Maybe you have this as well. Maybe this is 80, etc. Keep moving on. This is like 110. Excuse me. And then this, I guess, also must be 110, just according to stuff. Again, not drawn to scale, but these have to add up to 360 degrees. Okay. I'll just look at this one central angle for the next example of what we're going to talk about, which are intercepted arcs. We did arcs before, and they're the same thing, but now we're talking about what angles inside a circle do, and what happens with them. An intercepted arc is where basically, say I start drawing what I'd call a ray here out this way and a ray out this way. Okay, the intercepted arc has this arc right here, and it says, okay, I want to catch these 2 rays. So this ray starts drawing out. The arc says, I gotcha. And this arc starts drawing out, and this here says, I gotcha. And the arc that's formed in between these 2 points is called the intercepted arc. So it's just this blue guy right here. The intercepted arc is like pizza crust, again. But before we measured the pizza crust's length, now we're going to measure its degrees, basically how much of the circle is being covered out of 360. So if we refer to the previous example where we said the central angle is 60 degrees, if the angle is 60 degrees, the intercepted arc is also the exact same amount. So this intercepted arc here is 60 degrees. So they'll trick you with questions. They'll say, oh, okay, well, what's here? Let's do it here. Let's say, what's the measure of angle? Let's give this a letter E for this part. I think this is a D. What's this angle measure right here? Measure of angle AED. And maybe they only give you this 60 out here. So you say, okay, if this is 60, then this central angle is 60, and then you write that in. And this will help you because now you have this diameter right here, okay, which will say this is 180 degrees. This whole thing is 180. So this is the supplementary angle. This is 120 minus 60, which is, or 180 minus 60, which is 120 degrees. Or maybe they say, what's the measure of this entire arc? So you have to, of this entire arc. So you have to still do the same thing. If this is 120, then this is 120 as well. Intercepted arc. Pretty straightforward, and we'll go through practice through other notes and through homework, obviously. But that's the general idea behind intercepted arcs, is they're the same measure, and they're the pizza crust as well. Okay, you'll have major arcs and minor arcs. I'll go through minor arcs first because it's kind of more straightforward here. A minor arc is an arc that's less than 180 degrees. And by that I mean, so let's say the AC is a diameter here. Remember, a diameter is half the circle. So this thing is a semicircle. That's 180 degrees. So I want to find any arc that's less than 100. And I'll use my different colors here. DC is an example of an arc. And it's written like this, by the way. It's a 2-letter assignment. I go from endpoint to endpoint. DC is an example of a minor arc. AD, or DA, it doesn't matter which way you write it, is an example of a minor arc because they are less than 180 degrees. Remember, 180 is the semicircle. AB is a minor arc. BC is a minor arc. And can you find one more? You actually can. Take a look from D to B. This is also a minor arc. Okay, these are all less than 180 degrees. Because remember, the diameter indicates what would be 180. This was obviously less than 180. So those are minor arc examples. Anything, you go from one way to the other. I could have written CD. It would still measure the same amount, 60 degrees, for instance. Okay, pretty straightforward. Major arcs are arcs that are greater than 180 degrees. So again, if I draw this diameter here, AC, I need anything that would, like if I go from C to A, that's 180. I need something greater than 180. Like for instance, from C to B. Now the only thing though is that if I say from C to B, or if you tell me from C to B, that's a little ambiguous because there are two different directions we can go. We can go from C to B the way I was talking about, the major arc. Or you could be a little more simplistic and say, well, this is also C to B. So the question is, why can't I just say CB as a major arc here? Think about it for a second, and you come back and you say, well, if I say CB, I'm referring to this minor arc, just like I did over here, or BC, I guess. Okay. So major arcs, we need a 3-letter assignment for them. We need to use 3 letters because we need to be able to say, I want to go this way, I don't want to go this way. So in order to do this, you have to have a third point to reference. Let's say I said CDB. Now that I say CDB, this order matters. It says I go from C first, I have to hit D second, and then I have to hit B third. So in order for this to be a major arc, I can't go this way, CBD. It needs to be CDB. Another appropriate answer would be CAB, cab. From C, it passes D, yes, but it hits A as well. A is on that path all the way to B. So you can put CDB or CAB. You wouldn't put CDAB. Not that it's incorrect. It's correct, but you only have to use 3 letters. You just need to reference another point that is on that path. That way you know you're not going the other way. So a 2-letter assignment will automatically make you go the shortest route. Okay. A 3-letter assignment, it's neither here nor there. It's just that now you can specify which way you go. So, for example, let's look at this minor arc here from B to D. I could have put B, C, D, and I would not have been incorrect in saying that's a minor arc, but again, that's kind of redundant. I don't need the C if I know B to D, the shortest route here is this way. So I'd put BD instead of BCD. Same reason why I didn't put CDAB. Once I know what direction I'm going, I'm fine. I don't have to be any more specific. Find a couple more major arcs here. Looks like there's one the other way. CBD. Okay. I could have also put CAB. AD. There's also ADB. Okay, or again, because this was an A, or ACB. Doesn't matter which one. And then it looks like there is ABD. I feel like I got to sneeze. We'll see if I do. From A to B to D, also a major arc. Remember, they must be more than 180 degrees. Okay. Now there is one portion that I left out in this, and I want to write it in, so feel free to do this as well. Semicircles. That is a measure of 180 degrees exactly. So while the major arc is greater than 180 and the minor arc's less than 180, something like AC right here is exactly 180. So that's a major arc, and that's a semicircle. And the reason why I put it in the major arc section is because I need to make it a 3-letter assignment. Here's why. Let's say I just did AC. I said, for example, we have AC as an arc. Okay. If you do only AC, now I don't know which direction I go. Granted, either way is 180 degrees, this way or this way. But in fact, here let me undo all these. So, oh no, I'll keep them there. That way or that way, but I don't know which direction I want it to go. I could have gone this way or this way. So you need to do a 3-letter assignment like ADC or ABC, and now we can say which direction we want to go. ADC is this way because it crosses through D. ABC is this way because it crosses through B. So semicircle, you still need a 3-letter assignment just like major arcs, even though they are not greater than 180 degrees. You still need to indicate which direction you want to go. Okay, and yeah. So that's it for major and minor arcs. And now go through the meat and potatoes. That's the rest of this. Uh-oh. An angle. Oh, you know what? I had this stuff written before, and I was editing it, and I brought up an unfinished product here when I pasted this in. So let me erase this. Let me retype something for you here. I'm sorry about that. Because last time when we were on, I took this right from end number 13. I changed things around. And now we're working from there. So let me do something else. We're working on inscribed angles. And let me type something out for you. Here we go. Let's say it is an angle. I think I started to type that and then I stopped. An angle whose endpoints and vertex lie on the circle. And I'll explain what that means. I want to emphasize this. On the circle. Okay. If you call that a bullet point, I'll do one more. Its angle measure is exactly half the measure of a central angle with the same endpoints. Same endpoints. Okay, so I'll explain what both these mean. Let's go get that started. So an inscribed angle, like I said, an angle whose endpoints and vertex lie on the circle. So before I do an inscribed angle, let me get a central angle for you. Okay. Imagine you have a central angle, such as, because we worked with it before, let's do CD again. Okay. A central angle has its vertex lie in the center of the circle. Its endpoints lie on the circle. Okay, so when it says an angle whose endpoints lie on the circle, this will be the same thing. So an inscribed angle has endpoints lie on the circle. Its vertex, though, also lies on the circle. So in a central angle, it lies on the center. In a inscribed angle, however, its vertex lies on the circle, or its vertex lies on the circle. So let's pick another point here. The only reason I'm doing a new one, let's call it F, because I still want to call this E. The only reason I'm doing it over here instead of one of the other points is to emphasize what's on the back page. So here would be an example of an inscribed angle. Let me draw straight lines here, because I know that can look really bad. From D to F, and from C to F right there. So that is an inscribed angle. It goes from, its vertex is on the circle, shoots out, and its endpoints are also on the circle. Now the next portion of this says, well, what's the measure of it? And its endpoints, its angle measure is exactly half the measure of a central angle with the same endpoints. So you can see here, here's a central angle that is DEC. And I think we called it 60 degrees before. Okay. Well, this angle over here, DFC, will be exactly 1/2 the measure of the central angle that has the same endpoints. You can see these both lie in the same endpoints, and you draw an inscribed angle, you put the vertex somewhere on the circle. Outside of that, it becomes exactly half that measure. So that is 30 degrees. Okay. Now, we did a problem kind of similar to this. We did a Mars task problem involving dolphins, if you remember that. And what we talked about there was the fact that it doesn't matter where the vertex is on the circle as long as it is outside of this intercepted arc region. It's somewhere over here. I can draw new points. I can put it over here on B, like this. You see the purple there? Its vertex lies on the circle. Its endpoints lie in the circle. This measure is also exactly 30 degrees, if this is 60. This will be a second example that we do on the back, proving why it is what it is. And let's do a third one if we drew it as the diameter crosses through, just like the central angle here. And this one crosses through as well. This is also 30 degrees. This will also be done on the back side. We'll talk about these three examples, how we can prove and be sure that any of these inscribed angles, that's A with angle or vertex A and vertex B and vertex F, any of these three are exactly half the measure of this one central angle. Okay, so I'm going to have some drawings here, and I'm going to try and work with this as best as possible. Keep in mind, I didn't look at this again, so I'm going to be sure that I can get this right. I want to prove that, let's see, how to write this. We're going to prove that the inscribed angle is 1/2 the central angle. Okay, we'll do it in three different cases. We'll do it where the center is inside the inscribed angle, and by that I mean, here, I'll just draw it now. I gotta sneeze. 1 second. Excuse me. Okay. I'll do an example where the inscribed angle, or where the center is inside the inscribed angle. By that I mean, if this is my inscribed angle right here, okay, here's the angle, here's the center, it's inside of it. Okay? And then I'll do one where the center is outside of the inscribed angle, so I drew a new diameter to know exactly what point I wanted to go to, and we'll talk about what all this means. This one's going to get kind of weird, by the way. I don't know how easily you'll be able to follow along, but I'll try and do as best as I possibly can. It'll hopefully make sense. This one will be relatively simple, where the center is on the side of the angle. So basically, if I drew a diameter like this, the center is right there. It's on one of the sides of the inscribed angle like that, and it goes out like that. So we'll talk about those three different cases, and we'll say, okay, we'll prove that this angle, and this angle are not only all the same, but they are exactly half the measure of this. Well, I guess we're not going to prove that they're all the same, but proving that they're half the measure of the same exact central angle on all three would mean that they are the same. Okay, the first case here, I want you to look at, as I draw in green, this radius and this radius right here. Now, radii are congruent, okay? If radii are congruent, then I do have congruent sides in what looks to be a triangle right here. You see here in black, probably should have used a different color, but you see in black, I have a triangle. If I have two congruent sides in a triangle, that is called an isosceles triangle. Now, the only important thing about that I want to note, and I'm going to have to erase it and rewrite it, is that in an isosceles triangle, if you tilt your head, because normally we look at them this way, Two sides are congruent, and their opposite angles are also congruent. So even if I don't know what the angles are, I know that they're the same. So what I'm going to do over here is erase this. If these are congruent, then these two angles, if one of them is x, an unknown, I do not know what it is, this other one also must be x. Okay. Same thing applies over here. I'll go and draw it in green for you. If I have this radius and this radius, two radii are congruent. So again, congruent sides means I have an isosceles triangle right here. An isosceles triangle means that these two angles are congruent. Boom and boom. So I'm going to go ahead and label them. The only thing, though, is that I don't want to label them the same thing as the other triangle. I can't prove this triangle is congruent to this triangle. I only have side, side, and side, side. Side, side is not a congruency conjecture. So I'll give them two other labels. I'll call them y. Okay. So what I know right now is that my inscribed angle, this measure, is x plus y. So my inscribed angle is x plus y. Okay? Here's the central angle that I'm looking at. Remember, if this was a radius, this was a radius right here. Here's the central angle that I'm trying to find something else about too. Now, so far I don't have anything on it. I don't have the skinny on it yet, if that makes sense. But here's what I will do, and I'm going to talk about a previous concept here called remote exterior angles to figure out what these angle measures are. If I have angle measures, let's give real numbers because I think that you guys fare better with real numbers. Let's say this is 60 degrees and this is 70 degrees. Sorry, that was a bell. And they say, find this angle measure. Let's call it W. Okay. The way that most of you guys would look to do this is you'd say, well, I know that the angles in a triangle add up to 180, so let's first find this. And because these are supplementary, I can then do 180 minus that value, and then I'll get W. So you'd add up these two, you'd get 130. You'd say 180 minus 130 is 50. So you'd say this is 50 degrees. Sorry, I have sniffles. I'm having trouble here. Now, W, you'd say, well, W is taking 50 right here, doing 180 minus 50, and you'd get 130. You go, okay, cool, so W is 130. But if you really recognize something here, you'd say, well, wait a second. I've seen this number before. It's right there. And it looks like I just wasted time because I just did 180 minus the same value that I got to get the previous value that I had. So there's this concept, it's called remote exterior angles, and basically what it means is that if you have this exterior angle, you know what exterior angles are, right? If you have this exterior angle, an unknown, it will be the same value as the sum of the other two interior angles. So if there's an unknown angle, this angle which I don't know, I know these two. If I add these two up, these two will be exactly the same as this. Always, 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 as far as remote exterior angles go. So why am I bringing that up? Well, because I'm trying to find what this is. And this is a remote exterior angle for this triangle right here. If I do, say I'm looking at this orange triangle. You can see here I have two interior angles, which technically I don't know what they are, but let's call them X. And then I have one that I completely don't know. And then I have here an exterior angle. So if you just look at everything that's in orange here, okay, I'm trying to find this angle right here, and I have two interior angles that are not the third angle right here that's supplementary to this exterior. So if all goes the same with remote exterior angles, I just have to add the two other interior angles to get this remote exterior angle. So this angle will be x plus x, which is 2x. Okay, that's how the remote exterior angle works. And if you still didn't know that, you could still do the exact same process as you did before. Solve for what this angle is, which would be 180 minus 2x, and this would be 180 minus that value, and you'll be left with 2x again. Okay, let's do it from the other side. Now I'm looking at a triangle right here that's in, I guess, brown. Okay. And I need to find out this over here, this angle, and it's going to be the same thing. You work with remote exterior angle, and you say this angle will be the same as the sum of these two interior angles right here. So this is y plus y, which is 2y. Okay. Now going back here, we want to look back at our central angle, the whole thing. So if this is, well, let's make it a little thicker, make sure that we're for sure knowing what we're referring to here. AB and ACB, our central angle. That big red guy right there. I want to find out what this entire thing is. Well, it's 2x plus 2y. So our central angle is 2x plus 2y. So our proof here, again, this equation, we want to see that the inscribed angle is half the central angle. Is that true? Well, let me write down here, x plus y equals, distribute the 1/2 into 2x, you get x. Distribute the 1/2 into 2y, you get y. So x plus y equals x plus y. That does make sense. So this x plus y is exactly half the measure of this 2x plus 2y. Okay? So that one's a proof for the center being inside the inscribed angle. That's saying for sure how you can get how that one works. Okay, I might have some trouble explaining this one. I might even confuse myself a little bit. So before I begin this one, I want to draw the triangles that I'm referring to. First of all, this is the central angle, and this is the inscribed angle. I want to prove this is half of that. Okay. So as we do this, we're going to look at two triangles, and we're going to look at unknown, or I'm going to label x and y as I did before. So remember, and keep in mind here that when you have radii, two radii drawn out for central angles, you have made isosceles triangles. And that's a key portion of understanding all this anyway, of grasping all this. I'll take the green again. I'm going to draw a radius right here and right here. Okay? And when I do, I have again formed an isosceles triangle where these are the congruent sides. Therefore, this is a congruent angle, and this whole part, not just the purple. Here, let's look at olive green. This entire portion is also congruent. So those two right there, boom and boom. So let me erase the other green before, because I need to make sure I have what I need. So this portion, if we don't know what it is, let's call it x. Here's this portion right here, also x. These are two angles, which we're working with there. Actually, as I move on right now, just so you know what we're talking about, let me actually go back to that triangle. Let me redraw it one more time, because I want you to see the remote exterior angle that I'm going to refer to. That way I can have it drawn. So I'm drawing that fully out. The reason why is because here's my triangle, and check out the remote exterior angle right here, from green to green. Remember, this whole thing is x plus x. So this is 2x. Okay? So as I go and erase that green, I'm going to go ahead and write again that this is 2x. Okay? From here all the way to here is 2x. Okay? I know, I understand. It's pretty difficult to see. Okay, now I have one more triangle. Ooh, it looks like I didn't erase a line. Do that one more time. 2x right there. Now remember, we're going to try and find this, that central angle. Okay, another triangle that I see here is, check out the red, because I already have green kind of labeled here. So I have from here all the way out to here and back. Okay. I have another triangle here, isosceles, formed by two radii right there and right there. So I have two unknown angles, and these will be very small, so they'll be very tough to write. So because they are unknowns and they are notably different from the previous ones, I'm going to call them y. So if this is y, this is also y right there. Okay? Okay, so hopefully that makes sense there. I got y and y. It's these small angles right there. And I'm going to draw one more remote exterior angle here. If I extend this one fully out, okay, this is the remote exterior angle for these two other interior angles. If I add these y's together, outside here I will get 2y. Don't worry, I'll erase the red again, and I'll make sure this makes sense. Well, I'll make sure you can see what we're looking at. So this little portion right here is 2y. Okay, so as I erase these lines, I'm going to go ahead and write the y's back in as I need to. So see if you can see all these angles again as we work. So I have this little portion right here. This angle is y. All right, now this one won't be as important for me, but this one's also y. This portion right here was 2y. Okay, so let's go to blue. This is my inscribed angle. Remember, it's drawn from the purple. Because these are the endpoints right here. Here's the central angle. Here's the inscribed angle. So the blue right here is the inscribed angle. This blue right here is my central angle. In fact, I'm going to make it a little smaller because I want you to keep in mind that the 2x went all the way over here. You can kind of see green underneath the red. Okay. Here's my central angle. Here's my inscribed angle. Okay. Now, the inscribed angle, because we haven't done too much practice with this. If I have an angle like this, full angle. This full angle, let's say this full thing is 60 degrees. Let's say the small one is 20 degrees. Hang on a second. See, this is tough with the color thing. Let's say the green one is 60 degrees. And let's say the blue one is 20 degrees. And then I want to find what the red one right there is. Well, this is 40 degrees. Because this whole thing is 60, take out 20 of it, you're left with 40. Okay. So in this example, if I have the full thing, it looks like the full thing is x. Okay. This small portion is y. So the blue, if the full thing is x and I take out y, my inscribed angle is x minus y. Okay, see if that makes sense. I know that the blue is pretty big, so it's kind of hard to look at what we're talking about. But the x was this green right here, from here to here. The whole thing is x, and this little red portion here is y. If I take out the y portion, then I just have the blue, which is x minus y. Okay. Okay, now I'm trying to find this blue right here. Now this whole green right here was 2x. This red portion right here is 2y. If I want to find the blue, I take out 2y from 2x. So the central angle is 2x minus 2y. Okay? So again, our proof is to make sure that our inscribed angle is exactly half the measure of this one. Distribute 1/2 into 2, you get x. Distribute 1/2 into 2y, or negative 2y, you get negative y. And x minus y equals x minus y. Okay. Although these are different, things, x plus y and x minus y, that's no matter. The point is, you get exactly half the measure when you work on it this way. Okay. Now I have the third one. This is actually significantly simpler because I don't need an x and y. I really just need one of them. When the center is on the side of the inscribed angle, so we're drawing it out like that. And keep in mind, I'm going to go back here really quickly and look back at these drawings. So far we've looked at the example of blue, where the center is inside the inscribed angle. And we've looked at this purple example here, where the inscribed angle is outside, the center is outside the inscribed angle. Now we're going to look at a case of red, where you have the diameter going through the center, and that's also part of the inscribed angle. Okay. So let's go and look at that. And we'll say, okay, we got this purple here. I have a triangle, and let me just draw it in purple. Let me just finish it, because that's all we need. I use purple. I got, boom, a triangle here, the triangle, again, radii are congruent. Therefore, you have an isosceles triangle where you have congruent angle here and here. So let's go ahead and call those x and x. If those are both x, then the remote exterior angle right here is the sum of these two interior angles. That's not that angle. So x plus x is 2x. Okay, so here's my remote exterior angle for this triangle, or for this portion. So let me erase those purple parts that I just drew and rewrite those x's. So I have x here, and here I had 2x. Okay, sit there and think for a sec. We're practically done. This is the inscribed angle right here. This is x. This angle right here is my central angle. It's 2x. Remember, central angle's right there. This is 2x. X equals 1/2 of 2x. What's 1/2 of 2x? Well, x. So x equals x. Yep, that works. That one's the easiest one. I wanted to give you that one at the end to make sure that you got what we were talking about. I really needed this one to start, and this one flowed better with that one, so I wanted to make sure you got that. This one's obviously the simplest, but the other one's built up with that one just fine. So hopefully all that there made sense. Obviously, they're proofs. There are a lot to take in. What's extremely tough is when you have so much information, and it's like, oh my gosh, I'm not even really sure where to start with that. The important information, obviously, is knowing the inscribed angles are exactly half of it, and getting it from there. So before I sign off, let me really confirm and make sure that you get what I mean by the fact that inscribed angles are half the measure. And all inscribed angles are the same. So if I have the central angle right here, the brown part, ACB, this is my central angle. This purple one is half this measure. This red one is half the measure. This yellowish one, yellow, is half the measure. Okay. So like I said, this was on the Mars task, the dolphin problem. Not exactly like this, but a question was, how could I relate two angles? How do you know? The answer really is that they're congruent because they are inscribed angles. And inscribed angles are always congruent to each other. Okay. So that was the point of that, or that was the solution to that problem as we were doing it. Okay, so all of these things, it looks like I'm making a rainbow. I literally did not mean to do red, yellow, green, and stuff like that. All these, if this is 90 degrees, these are all 45. Every single one of them. Somebody did once ask in class, what's the measure of this right here then? Well, I'll tell you right now, it's not 45, and we'll talk about that another time. Okay, so a little bit overwhelming with the variables, but if you followed along close enough and you want to rewind it, you can. These are things that, again, I want to make sure that you know how to talk about them, at least this one right here, because they're arbitrary values. How do you assign them by isosceles triangles, etc.? Okay, signing off, though.